Math 1314, Tyler Junior College, Section 4.1, Exponential Functions, Application, Knowledge Retention. I wanted to do one more example for two reasons. Number one, the first two applications we've seen, modeling population and compound interest, were both examples of exponential growth. We knew that because the exponents were positive. But knowledge retention is an example of exponential decay. Let's say that you study something and then don't look at it again for a while. How much of it you remember, what percent of it you remember eventually declines. This function, f of x equals 80 times e to the negative 0.5x plus 20, models the percent of knowledge retained x weeks after learning the information. So in this one, we're going to evaluate and interpret two results. And then we got a little bit more of a theoretical question at the end, but we have the tools to answer it. So let's start with evaluate part A, evaluate f of 0 and interpret the results. F of 0 is easy to evaluate in this case because putting 0 in for the x gives us an exponent of 0. Negative 0.5 times 0 is 0. Well, e to the 0 power is 1. Now be careful. This 80 being multiplied occurs after the exponent is done because of the order of operations. Evaluate the exponent, evaluate e to that power, and then multiply. Well, e to the 0 power is 1. 80 times 1 is 1. 1 plus 20, excuse me. Let's try that again. Negative 0.5 times 0 is 0. E to the 0 power is 1. 80 times 1 is 80. 80 plus 20 is 100. Now, if you just wanted to put all that in a calculator, you're welcome to, but push your limits. See how much you can do without a calculator, especially when 0 is involved. So what does this 100 mean? Well, if x is the number of weeks after we're learning the information, then we would interpret this by saying, as soon as we learn the information, comma, we retain 100% of it. Now that's according to this model. I'm not saying that if you read something and close a book, you'll instantly remember 100% of what you read. If you have a photographic or an eidetic memory, then good for you, but most of us don't. But the interpretation would be as soon as we learn the information, because 0 weeks have elapsed, 0 time if you will, we retain 100% of it. I wonder what this is going to be after 1 week. Well, we would get 80 times e to the negative 0.5 times 1 plus 20. In this case, I'm going to go ahead and do the multiplication in the exponent, because multiplying times 1 is easy, and get e to the negative 0.5 plus 20. But this is going to require a calculator. And by the way, questions like this predates the technology that we're using now, meaning that sometime in the past, people had to calculate this stuff manually using techniques that are learned in a calculus class and are very, very time consuming. But lucky for us, we don't have to do that. All right, I invite you to try to put this in your calculator to see if we get the same answers. I'm going to round it to the nearest 1 decimal place, so 68.5% or 68.5. But let me reevaluate it just to make sure I didn't make a mistake. Got the same answer. All right, so what this means, if we interpret it, is after 1 week, we retain 68.5% of the information. Now this is probably assuming that we don't study or review or practice it again, that we just look at it and we walk away. So you ask yourself, if you study for a test a week before and don't ever look at it again, you want to go in armed with 68.5% of the knowledge? I wouldn't. All right, over time, what percent of knowledge is retained? Well, what do we mean by over time? I mean, as time progresses, as time moves on and on and on. Well, what happens to this value of x as time progresses? So you study something and then you just sit there forever. Isn't the x approaching infinity? So this is asking what happens as x approaches infinity. Now granted, we can't get to an infinite amount of time, but we can approach it by just getting closer and closer to it over the course of time. So we're being asked what happens as x approaches infinity. And by the way, this is a very theoretical question. But if we want to answer it, let's kind of think about the part of the function that the x is most intimately connected with, which would be this e to the negative 0.5x. Can you tell me something about that function's graph? Well, the base is e, which is greater than 1, but it's e to a negative power, which means that we're doing exponential decay. And I've already mentioned that we're doing exponential decay. And without the 80 or the 20, I know what this does. This gets closer to 0. As x approaches infinity, e to the negative 0.5x approaches 0. And if the graphing approach doesn't satisfy you, then I want to show you another reason why. I know what negative exponents do, don't you? A negative exponent says the reciprocal of the positive exponent. And so as the x gets larger, this exponent gets larger, which means this value gets larger, which means the fraction collapses down to 0. So we get the same result either way. So what does that mean here? So f of x approaches 80. Everything in there approaches 0 times 0 plus 20, which is 20. So that means, since we're measuring percentage, that means that over time, 20% of the knowledge is retained. Again, this is the model. It's not 100% accurate, but no model is. And that wraps up this section.